So next Berkeley Lab scientist is Jeff Urban, who thinks about energy in some new ways. Please welcome Jeff.
Good evening. My name is Jeff Urban. I'm a materials scientist up at the lab. And tonight I'm going to tell you about how I employ the concept of synergy when designing materials for energy applications. So first I have to define synergy, right? So synergy is the concept embodied by the equation I showed at the top of 1 + 1 = 3. So that is, when you put two materials together, you don't just get the linear sum, you get some new emergent functions. And just for an example from chemistry, here's good old sodium, metal you might be familiar with, and it's very reactive. So here's sodium being tossed into a pot of water, and you can see it's very, very reactive. And chlorine, some of you may know, is this sort of bilious, unpleasant gas. So you might say, if I put those two together, sodium and chlorine, what might I get? Sort of a toxic roaming metallic glass? No, one actually gets, right, I've heard several people in the audience say it, good old sodium chloride, salt. So this is a case of a materials synergy, where two materials are interacting and you get a new function that emerges from that, okay? So it turns out I definitely didn't invent this, and it's been around science for a long time. Nature does it really, really well. These are two materials that might be familiar to you. This is an abalone shell on top, and this is a bone in the bottom. And you think of these as really hard, tough materials, right? I mean, thank goodness, right, for those of us who fall off our bicycles with regularity. But it turns out they're not just constructed out of hard materials, which might be a little surprising. They're constructed out of hard materials and soft materials when you take a look at them. And it turns out you don't need just bricks to make a tough, resilient material. You need bricks and mortar. So hard materials and soft materials. And this is an example, another example from biology of a materials synergy, okay? So I applied this concept to materials for energy applications. And as you might see, hard materials and soft materials, like rocks, or inorganic materials as I call them, and soft materials, like plastics or polymers, are naturally maybe a little distrustful of one another. They don't naturally play together well, okay? So one of the great things about working in the lab and with the diverse set of sort of collaborators I get to work with is that I get to learn from everybody about the individual properties of materials and how to get them to play together nicely so that they're not so mistrustful from one another, and that we can build new materials with emergent functions, like biology does, or like the example I showed you at the top. So now I'm going to tell you about two examples where I've united those worlds of the hard materials, the inorganic materials, and the soft materials, the organic materials, to provide new function for materials and energy applications, okay? So the first one I'm going to tell you about is about energy storage. And hydrogen is a fuel that I've studied for a while and I like because when you combust it, it has no carbon. So when you run it and you run an engine off of it, the combustion product, if you will, is water. That's very benign and makes me sort of eager to study it. One of the challenges of working with it as a fuel is embodied right here. If you try to use it and you get enough of it that you can drive your car 300 miles, you need an enormous volume of it, and it's prohibitive to really have a reasonable vehicle. So you might say, well, let's squish it, right, down into a liquid. You can see even the word liquid doesn't fit on there. So it's a hard job to do and do correctly, right? So it turns out material has been very nice to us, and nature has been very nice to us, and metals of a sort, and I'm excited about magnesium, but I showed you a metal up at the top, sodium, that's very, very reactive. Metals chew up hydrogen. They love to store it. They store it very, very densely. They store it more densely than a liquid or a gas, which might seem surprising. Right. I have a question. There's a Q&A question coming, right? So, but it turns out they are very reactive, not quite as reactive as sodium. But they are quite reactive. So I'm going to explain the approach I took with soft materials and hard materials using this sort of cartoon. So Maggie is magnesium. That's the metal that I work with. And as you can see, Maggie is a very rapacious little creature. So I want Maggie just to eat hydrogen and form this nice stable metal hydride. But it turns out Maggie likes to eat fish and surfers and other things. So we put Maggie in a cage. Now in this case, it's a polymeric cage. So now we have a rather stable, well-behaved version of Maggie, magnesium, that can chew up hydrogen without getting into too much trouble. Okay? That's good. But we also want to be able to fuel our vehicles very quickly. So we need another trick in order to do this. So instead of having that volume contain one Maggie, I work with nanoscale materials, whereby, not to scale, we can fit many, many Maggies in the same volume. Therefore, we can chew up and store all that hydrogen very, very quickly relative to one big chunk of magnesium. So we've made this material, which is actually the magnesium or the Maggie in the polymeric cage. And you can see it, we're handling it here, trust me on this one, in open air, right in one of our chemical safety hoods. And it's completely stable. It's totally, totally harmless and stable. And we've left it there for 6 months and done studies on it, and it's relatively unaltered. And the proof is in the pudding at the end of the day. Now, this is a chart of how much hydrogen this material soaks up versus time. And magnesium all by itself with no help and a very large relative to nanoscale. These are microns, so it's 1,000 times more large in scale. It's very, very slow. It doesn't even take it up noticeably on the order of an hour. But the nanoscale hydrogen, Maggie, ITER, in the composite is actually very, very fast. Okay? So another area and another realm of energy science that I'm excited about, and I've realized these material synergies, is in thermoelectrics. Now, it might be a new word, not quite as popular as photovoltaics and other things you've heard of. But they tell you what they do right in the title. These are materials and devices that change thermal energy, thermo, into electrical energy. It's a pretty powerful concept, right? Put this device near a fire and out you get electricity. So this is a very important thing because engines, like car engines, or really any energy you can think of, whether it's a glass-blowing plant or industry, are not perfectly efficient. Thermodynamics tells us that. And how inefficient are they? Well, just your standard car engine. If you think about putting in 100 units of fuel, only about 30% of that goes to running the car, kinetic energy. The rest of that is actually lost as waste heat. And you know that because your engine gets very, very warm, even if you just drive down the street to Berkeley Bowl or something, right? It's surprising how hot they get. So thermoelectrics would have the ability to take that waste heat and change it into useful electricity to mitigate the energy demands of the car and power electronics and do things like that. Now, it's just for vehicles, but you can imagine the broader implications here. Now, the problem is that most thermoelectric materials are built out of sort of hard rock-like things. And heat goes out in every direction. So it's hard to capture, okay? So we've built new kinds of materials for thermoelectrics that are built out of both the rocks and the polymers. And they're amazing in the fact that they can conform to any shape you can imagine, like wrapping around this engine to grab heat very efficiently in all directions, and to actually use that for some of these sort of really interesting and intricate and difficult to use applications for standard materials. So it's a case where this material synergy has allowed us to realize a totally new function in a material that you really couldn't do with any of them on their own. And these are the kinds of problems that I get excited about, and it's why I like working at the lab and on fun topics like this. Thank you.